Hello everyone, here is my report for the first lab assignment. We will look at the motion of an object traveling at constant velocity and the analysis of this motion with the help of tracker. We will then assess the readings obtained from this analysis with the observations predicted by the computational model. For the purpose of this experiment, I have selected a standard rubber ball and carried out the analysis by applying Newton's second law of motion to predict the velocity and position of the ball with respect to time. We begin with loading the video in Tracker in order to carry out its experimental analysis. We select the range for the analysis and set the starting and ending frame numbers accordingly. Please note that the ball moves from left to right and it is considerably smaller in comparison to a soccer ball. Next, we check the clip settings to make sure that the video frame rate is 30 frames per second. I then calibrate the object using the calibration stick. The diameter of the rubber ball is about 6 centimeters, so I'll go ahead and enter that value as a dimension of the calibration stick in SI units, that is meters. Next, I select the coordinate axes. Here the origin is set at the center of the ball with the positive x-axis along the direction of motion of the ball. Once all the above settings are applied, I move on to the tracking of the ball's position within the selected range. The positions of the ball at different time steps are recorded at the bottom right side in tabular form. The final tracking obtained is in the graphical pattern displayed at the top right. We note down the following values from the experimental data that we obtain. The initial velocity can be calculated by dividing the difference between the positions and time at the first two time steps recorded by Tracker. Now we will take a look at the computational model for this analysis. Since the motion is at constant velocity, I simply edit the Python code lab1start.py. The mass of the rubber ball is about 50 grams, so I assign that value in SI units, that is kilograms. The initial conditions, that is the initial velocity and position of the ball, are changed by referring to the values that we noted down previously. The starting time and time step delta t can be assigned the values of 0 and 0.01 seconds respectively. Similarly, I change the value of the final time, that is the time for the last observation in Tracker, to 1.3 seconds in the condition for the while loop. Next, I edit the code for predicting the values of velocity and position of the ball. The net force vector is considered to be 0. I change the code steps to represent the equations for velocity and position of an object according to Newton's second law of motion. Once the code lines are edited, a computational model will be ready. In order to generate and observe the outputs of the model, I uncomment the respective code lines. We can observe the motion of the object and its change in position with respect to time. We also need a CSV file to compile the values predicted by the model in the form of a spreadsheet. I change the name of the CSV file to generate a separate spreadsheet for the same. Now that our computational model is complete, we can run the code and observe the output that it generates. Now I copy the experimental values obtained from Tracker to compile it with the data predicted by the computational model in the spreadsheet. Can now generate a chart to compare both the model and experimental values graphically. The graph obtained for the change in position with respect to time for my analysis is something like this. We can observe that the experimental and predicted values match to some extent. While the predicted values are in a straight line, the experimental values deviate a bit and are a little curved. This happens because the net force acting on the object is not always zero practically, although the model considers it to be so while predicting the motion of the object.